So at this point, we've pointed out that the rationals are sitting inside of the reals and that they're dense inside of the reals, and that in some sense the reals are the rationals with all of the holes plugged. We haven't really done anything with that fact. In particular, we haven't really seen any real numbers that aren't rational numbers yet. So let's talk about why you can do that and why the stuff that we've seen so far helps us do that. And the simplest way to talk about this is to say, hey, once you have the real numbers and you have the completeness axioms and density and so on, you can use that to find solutions to equations, and in particular to find that certain numbers exist which aren't sitting inside of the rationals. So let's do a simple version of that to prove that the real number square root of 2 exists, and furthermore that it's not irrational. All right, so the first thing we've got to say is, what do I mean by the square root of 2? Well, square root of 2 is some number that satisfies square root of 2 whole thing squared is equal to 2. Okay, so that's what I mean by the square root of 2. It's some number that when you square it, you get 2 back. And so when you write it that way, it's not so obvious that any such number should exist. And of course, we sort of know, although we haven't proved it yet in this class, that square root of 2 exists and is not an element of the rationals. Okay, so we want to figure out, hey, is that really an element of the reals? And how would you check something like that? So I'm going to look for it in sort of the obvious place. I'm going to let S be the collection of real numbers between 0 and infinity, satisfying x squared is less than or equal to 2. And then I'm going to let A be the supremum of S. And we sort of know in the back of our heads, of course, that this element A is going to end up being the square root of 2, but we haven't assumed that, and we haven't gotten there yet. Okay. So now let's sort of build up some facts about A and S. So the first thing to point out is that certainly 0 is in S, so S isn't empty, right, because 0 squared is less than or equal to 2. On the other hand, for all x bigger than 2, x is not in S, right, because 2 squared is certainly bigger than 2, and 3 squared is bigger than 2, and so on and so forth. And so the first thing that we know is that the supremum A exists, and furthermore, it's somewhere between 0 and 2. Okay, great. Now that we know that A exists and it's sitting inside of this bounded interval, we can try to narrow down what A can actually be. So first of all, let's assume that A squared is actually strictly bigger than 2. Then we're going to look at these numbers that are a little bit less than A. And we're going to check that those little numbers, A minus 1 over M squared, are also going to be bigger than 2. So let's check how we do that. So we consider A minus 1 over M, then A minus 1 over M squared, after a little bit of algebra, is bigger than A squared minus 2A over M. Okay, we also could have used Bernoulli's inequality here. So by the Archimedean property, there exists some M so that 2A over M is less than A squared minus 2. And therefore, A minus 1 over M itself is an upper bound for S, and of course, it's strictly less than A. Okay, so what have we done? We've shown the following. If A squared is strictly bigger than 2, then there's this other number, A minus 1 over M, that's still an upper bound for S, and it's less than A. Therefore, A was not the supremum to begin with. So we've gotten a contradiction. So what we've shown at this point is actually A squared is less than or equal to 2. That's sort of the conclusion of this chunk of the proof. Now let's go in the other direction, and we're going to do exactly the same thing, so I'll go a little bit more quickly. Suppose that A squared is less than 2. Then we want to look at a number A plus a little bit, A plus 1 over M. And we do the same algebra, and what we find is that A plus 1 over M squared is less than, say, A squared plus 5 over M. I'm not being terribly careful about this bound. So we can use the Archimedean property again to find a value of M so that this A squared plus 5 over M is not too large, in particular so that 5 over M is less than 2 minus A squared. When we've done that, when we've gone just a tiny bit above A, then A plus 1 over M is still sitting inside of S, but obviously A plus 1 over M is bigger than A. Therefore, A is not an upper bound at all, right? Because it's not bigger than A plus 1 over M, and so we have a contradiction as well. So using basically the same argument we've just shown, that A squared is bigger than or equal to 2. So what do we have? A exists, and it's a real number. It's somewhere between 0 and 2. A squared is less than 2. A squared is bigger than 2. And so if A squared is less than 2 and A squared is bigger than 2, then actually it better actually be equal to 2, and so square root of 2, which is the supremum of S, is sitting inside of the reals. So that's a little bit of a messy argument, but actually the same argument is going to work to get all sorts of other numbers which aren't sitting inside of Q. And there's sort of a general proof strategy, right? If you want to find a number that has a property like this, then you let S be all of the numbers that sort of satisfy that equation, and also all of the numbers that are sort of on one side of that equation. And then you can play exactly the same game and check, hey, if you don't have an exact solution to the equation, well, then you can find sort of numbers that satisfy that inequality, which are close to the number that you're interested in. Okay, so you can check for yourself. You can prove that the 7th root of 3 exists using exactly the same argument as I did here, and it's maybe not such bad practice to do that. It's also worth pointing out, in case you haven't seen this argument before, that actually the square root of 2 is not sitting inside of the rationals at all. So we've actually really found a new number here, one that's not sitting inside of the rationals. The proof here is completely unrelated to anything else we're doing in the class, but it's relatively short, so I'll give it anyways. Let's assume that root 2 is sitting inside of the rationals. So that means you can write root 2 is equal to m over n for some pair of integers m and n that are relatively prime. That is, they have no common prime factors. So let's just rearrange this. We get 2 is equal to m squared over n squared, so 2n is equal to m squared. 2n squared is equal to m squared. Therefore, m is actually even. And so 2n squared is equal to 4k squared, and so n is equal to 2k squared. So then n is even as well. But that means that m and n are both even, which is a contradiction because we assumed that they were relatively prime. Okay, so that's just sort of a quick argument that square root of 2 is not sitting inside of the rationals.